In the name of Almighty God, I'm Mahsa Sankashi, and today I want to talk about anisotropic heat transfer through woven carbon fibers. Heat transfer through woven carbon fibers is anisotropic, meaning it depends on a direction with much higher conductivity parallel to the fibers that perpendicular to them. This is because the carbon fibers themselves provide a continuous path for heat, while the non-conductive polymer matrix and the gaps between fibers hinder heat transfer in the true thickness direction. The overall thermal conductivity is also affected by factors like fiber volume fraction, yarn tightness, and the specific weaving pattern. And what about the heat transfer characteristics? The first one is parallel to fibers. Heat conducts efficiently along the length of the fibers, which are like continuous pathways for heat. The next one is perpendicular to fibers. Heat transfer is significantly lower because it must pass through the less conductive polymer matrix and the gaps between fibers, hindering heat flow. The next one is factors influencing conductivity, and the next is fiber volume fraction or FVF. Higher FVF or fiber volume fractions lead to greater thermal conductivity by reducing the amount of matrix and increasing fiber to fiber contact. Yarn tightness is the next one. A tighter yarn spacing reduces the distance for heat to travel between fibers, increasing conductivity. And the next one is a weave pattern. Different weaving patterns like twill or non-crimp fabrics affect the packing of fibers and can alter the true thickness thermal conductivity. And what about the applications? The first application is high conductivity, used in electronics for heat sinks and other components to dissipate heat efficiently. And the next one is low conductivity, used as an insulator where heat retention is necessary. The next one is controlled heating. Can be used in applications like composite manufacturing to generate heat via Joule heating, prompting curing of the matrix material. The aim of this simulation is to determine the heat transfer properties of biaxial carbon fabrics of different architectures, including non-crimp stitch bonded fabrics, plain, twill, and stain woven fabrics. The specific heat capacity was determined via DSC or differential scanning calorimetry, a novel method of numerical analysis of temperature maps from a video using a high-resolution thermal camera is investigated for the measurement of the in-plane and the transverse thermal diffusivity and conductivity. They determine thermal conductivity parallel to the fibers of a non-crimp stitched bonded fabric agrees well with the theoretical value calculated employing the rule of mixtures. The presence of voids due to the yarn crossover regions in woven fabrics lead to a reduced value of transverse thermal conductivity, especially in the single pillar measurements of this study. Heat transfer plays an important role in all stages of composite manufacturing. Heating in performing is used to melt the thermoplastic matrix or binder so the fabric can be deformed and the layers consolidated, and also cure the adhesive binder for thermosetting binders. Performing takes place in single SDF or double diaphragm forming (DDF) or matched tool forming. Mainstream composite manufacturing techniques include autoclave processing, resin transfer molding or RTM, vacuum assisted resin infusion or VRRI, automated fiber placement or IFP, thermoforming, and pultrusion. Controlled heating is used in all techniques in combination with pressure or vacuum to reduce the matrix viscosity to facilitate resin flow, impregnation, or bleeding and layer consolidation, as well as to affect solidification via curing for reacting resins, especially thermosets, or cooling for thermoplastic matrix. Product design and process optimization in composite manufacturing is usually conducted via computer simulations in which the heat transfer equation is of particular significance. The thermal properties of the composite material and the contact resistance at interfaces are key properties in the heat transfer equation that need to be measured and inputted in the computer algorithms. The role of mixtures or modifications could be used to predict the density and specific heat capacity of a composite material, both of which are isotropic properties. The specific heat capacity is also measured using differential scanning calorimetry or DSC. However, it is more difficult to determine the thermal conductivity, which is a property depending on the fiber direction or the direction of nano-reinforcements for particulates with an aspect ratio such as carbon nanotubes, nanofibers, and graphene or graphene oxide, which may be either randomly orientated in usual mixing, casting, coating via Dr. blade or spraying techniques, or orientated via electrophorese or electrospinning. For example, for unidirectional reinforcements, the rule of mixtures may be used to predict the thermal conductivity in the direction parallel to the fibers. As heat transfer is dominant through the laminate's thickness, the thermal conductivity in the direction transfers to the fibers is critical. It can be predicted by the harmonic mean, also known as the inverse rule of mixtures, but that indicates the lower bound on the composite conductivity. The next best constitutive relation for the thermal conductivity of a composite transfers to the fibers is given by this model, where Km and Kf and T are thermal conductivity of the matrix or air for dry reinforcement, and the next one is transfer thermal conductivity of fibers respectively, and Vf is the fiber volume fraction. It must be said that a range of values have been reported for the transfers and axial thermal conductivity of carbon fibers, depending on precursor manufacturing, road treatment, and temperature. Modeling becomes even more complicated for multilayer or woven fabrics, pointing to the necessity of measuring the thermal conductivity. The main issue is the measurement of thermal conductivity is to account for the contact resistance. Standardized and devices have been used for the measurements of the transverse and in-plane thermal conductivity respectively. They both include two samples sandwiched between a central tin heater and two outer heat sinks. A known heat flux is applied and temperature is measured at the heater and each heat sink. From these values and the dimensions of the samples, the thermal conductivity is determined according to the Fourier's law. The contact resistance may be reduced by immersion in glycerol, but this would not be recommended for dry fabrics as the glycerol would infiltrate and loosen the fabric structure. In fact, as glycerol is still used for the rest of the contact surfaces, researchers sealed the dry fabric samples to avoid glycerol infiltration. They found that the true thickness, thermal conductivity of non-cream carbon fabrics and twill woven carbon fabrics increased with increasing fiber fraction up to woven penetrol was reached at about Vf is equal to 0.43 and 0.50 respectively, which might be attributed to the corresponding increase in contact points and contact area up to the packing fraction. Beyond these studies, there have been no further developments in the techniques for measuring the thermal conductivity of textile in composite materials. The use of infrared or IR thermal mapping may be a better method to focus on the heat transfer inside the sample area only to determine its thermal conductivity and then move to the interface to determine the interface contact resistance. This novel technique has been recently developed in our group to measure the thermal conductivity of a thermoelectric wearable textile and the individual materials of its composite structure. Hence, this latest novel technique will be investigated in this study to determine both the true thickness transfers and in-plane conductivity of fabrics in this form. In particular, with regard of the diaphragm forming process as illustrated here in this simulation, the aim of this study is to determine the heat transfer properties of 90 degrees of biaxial fabrics of different architectures, including a non-crime stitch bonded fabric plate, twill and stain woven fabrics, and compare the values with the predictions of a Clayton's model. And what about the materials and methods? The first one is material. As you can see here in the simulation, displays the micrographs of the four fabrics tested in this study, where these images were obtained using a digital microscopic in transmission mode, a biaxial non-crime carbon fiber fabric, and the NCF 300 biaxial of an areal density of 300 gram, and a measured uncompressed thickness of 0.70 millimeter. The NCF consisted of two identical piles at 90 degrees orientation held together with a polyester yarn in a straight plain stitch pattern with a pitch of 5 millimeter. A plain woven carbon fabric A0186 000 and with an areal density of 199 gram and a measured uncompressed thickness of 0.27 millimeter. And the measurement of the specific heat capacity. The specific heat capacity of all the fabrics and the silicone rubber diaphragm was determined via differential scanning, colorimetry (DSCM) experiments using a TA instrument DSC Q100 1000. A DSC scan was carried out in the temperature range of 15 to 140 degrees of centigrade at a rate of 5 degrees of centigrade and the next topic is measurement of the thermal conductivity. The thermal diffusivity was determined from the analysis of temperature map videos captured using a thermal imaging or camera FLIR R300 with a high magnification lens, 25 micrometer resolution. And here in this simulation, the two sets up for the measurement of the transverse through thickness and longitudinal one of the in-plane directions, thermal diffusivity. For the measurement of the transverse diffusivity, the fabric was placed on the hot plate covered by the silicone rubber diaphragm and secured in place using a weight on the top. The camera faced the free thin side of the fabric as shown here for the measurement of the longitudinal thermal diffusivity. The fabric was partly placed on the hot plate and was partly left hanging out of the plate as in a cantilever plate setup, with a chin support at the end so the fabric would remain flat during the experiment. The camera faced the free thin side of the fabric between the hot plate and the support. Initially, the hot plate was at room temperature when the materials were assembled on top of it. To set up the camera and find the correct focus point, a piece of paper was used to not preheat any of the materials. The location was then marked so the fabric could be placed onto the hot plate in the correct position and was not preheated before the experiment began. During the experiment, the hot plate was heated from room temperature, and temperature room is equal to 20 degrees of centigrade to 100 degrees of centigrade, mimicking the conditions in the performing where heating to 9 to 100 degrees of centigrade is required to activate the binder. The temperature images from the IR camera were video recorded at a frame rate of 30 Hz. All post processing was carried out using the FLIR tools plus software. The hot plate temperature was monitored using type K thermocouple and recorded on a picothermocouple data logger for each type of fabric and conductivity measurement. Two or three repeat experiments were carried out. The following heat transfer equation was applied for the fabric face opposite the camera, where T is the temperature, TA is the ambient temperature, T is time, and xi is the dominant direction of heat flow. The transfer direction xt for here in this picture measure the true thickness transverse conductivity kt and the longitudinal direction xi for this simulation. And rho is the fabric density calculated from the areal density of fabric, and rho r divided by the fabric thickness as measured during the experiment with a micrometer and the IR camera photographs. While it is expected that a fabric is uncompressed in the measurement of the longitudinal conductivity, it is compressed in the measurement of the transverse conductivity. The fabric volume fraction is also calculated from its density, considering that it consists of carbon fiber, ignoring the stage and binder mass of a density of 1760 kilogram cubic metric. Cp is the specific heat capacity of the fabric measured from the DSC experiment. H is the heat transfer coefficient between the fabric and the air, and I is the boundary layer length of this heat transfer due to natural convection. Um, and the equation here in this heat transfer in solid module was linearly fitted to obtain the thermal diffusivity from the gradient of the line where a constant rate of heat loss to the ambient environment was assumed represented by the intercept of the linear fit. Using the Cp value obtained from the DSCP experiment, the transverse and longitudinal thermoconductivities were determined from the transverse and longitudinal thermal diffusivities respectively. According to the discretization method in this equation, the method of determining the thermal diffusivity and hence thermal conductivity is second order accurate with regard to the space interval between two consequent points in each triad of points j minus 1, j and j plus 2 selected for the numerical analysis. And what about the result and discussion? Result of the specific heat capacity. Here in this simulation, the results of the DSC experiments in the form of a specific heat capacity Cp as a function of temperature, the results clearly show an almost linear relationship of the specific heat capacity as a function of temperature for most parts of each curve. The dip at the end of the Cp graphs indicates the end of the test a little before 140 degrees of centigrade. The silicon rubber seems to have the highest Cp value, varying from 1.3 joule and etc. which agrees with the literature. According to the material specifications, the polyester stitch has a glass transition of 80 degrees of centigrade and melting point of 260 to 270 degrees of centigrade, and the binding agent has a melting point of 110 degrees of centigrade, and no endothermic effects indicating glass transition of the stitch or melting of the binder are visible in the DSC curves, which may be due to the fact that the amount of binder below 5% and stitch in the sample pan on the DSC instrument are negligible in their effect on heat flow. And what about the results of thermoconductivity? All results of thermoconductivity are summarized in this the table of this CSV Excel. And first of all, the analysis for the longitudinal thermoconductivity parallel to the fibers of one layer on of NCF 300 biaxial is presented in this simulation, with the XY axis of the plot defined by the relations in here. Triads of points were selected in the bottom ply as depicted here, which where parallel horizontal fibers were facing the camera. The linear fit of equation in this simulation yields an elongational thermal diffusivity of 6.8 multiplied by 10, uh, which after substituting the density and specific heat capacity values yields a value for the elongational thermal conductivity, and taking the value of the axial thermal conductivity of T is equal to 300 carbon fibers as Kf, A is equal to 8.4 watt, and measured of Vf is equal to 0.35. The rule of mixtures yields a theoretically calculated KLL is equal to 2.94 watt, which is very close to the experimental value, also taking into account the experimental errors. The next step is the determination of the transverse conductivity for all fabrics, the analysis of which is presented here, and the results are presented in this numerical result, starting with NCF 300 biaxial, a transverse thermal diffusivity of 0.15 multiplied by 10 to the power of minus 6, determined from the gradient of the linear data feed yielding a thermal conductivity. It must also be noted that the heat conduction measurements were performed on a single layer of each fabric in direct contact with the flat hot plate and the flat diaphragm, which leaves larger gaps compared to large stacks of fabrics which would benefit from the nesting of yarns and other microstructural features that would increase the overall number of contact points and contact area between individual fabric layers, yielding higher values of transverse thermal conductivity. Indeed, this was observed by A.I. Haig and his colleague when they increased the number of fabric layers in the stack, especially when they secured the assembly with true thickness stitching in three-dimensional fabric architecture. And what about the conclusion? The heat transfer properties of single-play fabrics were measured using DSC to determine the specific heat capacity and temperature maps from the video of an IR thermal imaging camera to determine the longitudinal or parallel to fiber and transfers tau thickness of fabric. Thermal conductivity. The DSC in the temperature range of 30 to 138 degrees of centigrade yielded Cp values in the corresponding range of 1.3 to 1.4 joule for silicone rubbers used as diaphragm material in the performing. And 0.12 to 0.25 joule gram and Kelvin for the unidirectional carbon NCF, agreeing with the data in the literature. Biaxial carbon woven fabrics exhibited higher CP values than the unidirectional NCF in the corresponding range of 0.67 to 0.82 joule divided by gram Kelvin for the NCF 300 biaxial. A heat transfer from a layer of a carbon fiber cluster at low Reynolds number. The heat transfer coefficient from a cluster of a very fine carbon fibers was measured by a transient test method. Air was heated by a heat composed of a cluster of 8 micrometer diameter carbon fibers. The input to the heater was an electric pulse, and the transient gas temperature was measured and compared with the numerical results with an assumed heat transfer coefficient. The obtained heat transfer coefficient was compared with that of single fibers and packed beds for a wide range of Reynolds numbers. The heat transfer coefficient of a fiber cluster showed a much smaller value than that of a single fiber at very low Reynolds number. This result implies that the heat transfer coefficients of fibrous or porous media at their low Reynolds numbers don't approach those of a single particle or fiber. Correlations of heat transfer were investigated on the basis of internal flow rather than external flow, and it was found that the non-uniformity of the fiber location and cohesion of fibers strongly affect the heat transfer characteristics. And thermal conductivity modeling and characterization for woven fabric polymer composites modified with nanofillers. Woven fabrics polymers or WFP composites inherently possess a low thermal conductivity, which limits their applications in thermal management. Three types of nanofillers, including particle type nano zinc oxide, rod type carbon nanotubes, and flake type graphene nanoplatelets or GMPs, are selected based on their geometrical morphologies. Their effect on the thermal conductive characteristics of WPF composites are systematically analyzed. Based on the effect medium theory or EMT, an analytical method is proposed to predict the effective thermal conductivity or ETC of WFP material system. This strategy quantifies the influence dimensions and the mass fractions of nanofillers on the ETC of material system. Single-sided constant temperature or heat transfer experiments show that the average steady state temperature of the specimens increases with increasing nanofillers mass fraction, reaching enhancement of 18.71% for 3 watt percent GNPs and 10.45% for 3 watt T and 2.57% for 3 watt percent for nano ZNO. The effectiveness of the analytical method is validated through finite element method analysis and experiments. The interphase thermal conduction models are established based on the geometrical morphologies of the nanofillers and the interphase bonding states in WFP composites, which explain the heat transfer mechanism of WFP composites modified with different nanofillers. Thermal study of carbon fiber reinforced polymer composites using multi-scale modeling. The layer fibers of carbon fiber reinforced polymer composites exhibit low thermal conductivity or TC throughout their thickness due to the poor TC of the polymeric resin. Improve the heat transmission inside the hydrogen storage tank during the filling process can reduce further compression work and improve the heat insulation can minimize energy loss. Therefore, it is crucial to understand the thermal properties of the composites. This simulation reports the thermal behavior of plain woven CFRP composite using the simulation at the micro, meso, and the macro scales. The TC was predicted numerically and compared to experimental findings and analytical models. Good results were found using the approach of multi-scale modeling. A parametric study was carried out to analyze in depth in the influence of certain variables on thermal properties. The study revealed that both fiber volume fractions and temperature significantly influence the TC of the composite, with the interface fiber matrix thickness following closely in terms of impact. The matrix porosity was found to have a relatively slighter impact, particularly within the porosity range of 5 to 15%. Composite materials reinforced with carbon fiber are relatively widespread and their application is increasing. These high performance composites are lightweight, robust, and resistant to corrosion. Beyond these inherent qualities, carbon fiber reinforced polymer or CFRP distinguishes itself through exceptional fatigue and creep resistance, particularly when subjected to harsh environment conditions and varying loads. These unique attributes position CFRP as a superior choice among fiber-reinforced polymer or FRPs. In the realm of applications, the CFRP is at the forefront of diverse industries, playing a pivotal role in aerospace, automotive, construction, and sport equipment. Its prevalence in these sectors underscores its versatility and underscores the material's significant impact on advancing technology and engineering solutions. Most composites developed in previous years were designed and manufactured to enhance mechanical features such as toughness, stiffness, and strength. However, high thermal capacity, especially the ability to endure high temperature and remove heat quickly from thermal sensorial equipment or heat exchangers is becoming extremely relevant. In the literature, there is a wealth of studies on the mechanical characteristics of composites. Thermal assets, on the other hand, are addressed in fewer accounts because the heat conduction qualities of carbon may be modified to fit the demands of a specific engineering application. It's among the most adaptable materials for thermal control. Thermal conductivity or TC is increasingly being given more thought in order to broaden the applications of composites. When reinforced polymer composites are employed, they face several challenges. In fact, they are frequently subjected to a quickly change temperature setting. As a result, thermal stress is created, which has considerable influence on composite stiffness and strength. Considering that polymer composites are frequently thin, the simplest way to eliminate heat from a composite structure is through its thickness direction. Nonetheless, the researcher reported that the ratio of transfers in plane thermal conductivities may be adjusted from 30 to 130 and restricting heat transport in the thickness direction. The thermal stress generated by temperature changes has been shown and have significant influence on material failure. As a result, it is critical and necessary to explore the heat conductivity of composite and many researchers have considered various techniques for predicting the heat transfer and thermal properties of such composites. Most anisotropic composite material research has concentrated on mechanical properties, with just a few models developed to estimate heat conductivity characteristics in several directions. Mechanical parameters that have been experimentally established can be validated using recently reported analytical models. However, there are just a few models for TC that are available for casual verification. Most study predicts effect thermal conductivity or ETC across a material thickness using the law of matrices. However, heat conductivity along the composite fibers orientation may be easily anticipated. Models that predict transverse conductivity are mostly dependent on the geometrical configuration of the reinforcement in the investigation. The unidirectional reinforcement model of the Charles and Wilson and Maxwell were employed, where a grip angle was included with these models to account for the undulation phenomena of the analyzed woven fabric. And here you can see the contour simulation, and I have used the curved linear coordinates as a physical module, epoxy, carbon, and carbon infinite element domain, and heat transfer solid as another physical module. And after that, we made a mesh, and you can see that our vector field coordinate system, temperature and middle slice. I can see the carbon fiber here that woven together, and how the temperature expand through these woven threads. Thank you so much for watching my video until the end, and also you can download this simulation from my github.com/masterscript, and the name of this simulation is carbon fibers.